any type of issue with Golden Gate processes. And I can't stress that enough. I added in the bottom here is the database alert log. So again, I'm talking Oracle to Oracle. If you're doing Oracle to DB2 or DB2 to Oracle, I have to be honest with you, I know nothing about DB2. So if they have something like this, great. If not, I guess we'll have to look it up. But for Oracle to Oracle, you must include the alert log on the target database that the replicator client data is. Okay? On the target, the source database, we only really need to look at the alert log if we're using the integrated capture extract. Okay, because it's using log-miner server processes, the alert log can show us very valuable information with regards to which log files have been mined, how long it takes to log, to mine each log file, and any pertinent database errors that you'd normally be looking at for your Oracle database. So those three files are the three files that you always check on for performance issues and diagnostic issues for going. So when a processor bends, which aborts, the first place you go to is the report file, the ggserr.log file. Always the first place you go. Okay, if it's performing slow, you still look at those, and again, your alert logs on the target or on the source if you're running integrated capture. Talk a little bit more about this integrated capture mode. Again, I'm not going to talk about the details of how it works because GGtuning did a real nice presentation on that on Monday, right? About the architecture and how it works. So that should be available to download now. It should be on OpenWorld site too. But basically, because that's now using some processes within inside the database, the log-miner server process, we have two new data gathering points. The first being this thing called the integrated capture health check. Basically, it's a SQL script written by the distinguished product manager Pat McElroy. That basically a SQL script that goes through the database and gathers a ton of information with regard to the log-miner configuration, log-miner server configuration within that source database. What that creates is it creates an HTML page, which is very easy to then browse through to find out what your configuration. And it includes some performance statistics also, which is very, very helpful. Link to that, again, it's detailed in that Oracle support note. How to download it and how to look at it. Streams performance advisory, and this is a big misnomer. So the log-miner server processes with the log-miner preparer, the log-miner reader, and the log-miner builder, we use those, or I should say we use something like those in Streams architecture. So currently we have this thing with SKDB, the Streams Performance Advisor, that we use within Streams Performance Tuning. And what it is basically, it's a little executable SKDB that runs against your target, your source database, and it gathers key bits of data for each one of those log-miner processes. So for the reader, preparers, and the builder, it'll show you the percentage of time it is spent idle, doing nothing. It'll show you the percentage of time spent busy or waiting on an event. So if you see an event that shows 100% on log file sequential read, you know that you possibly have an I/O issue that your log file reads a little too slow. And then we have this other percentage, which is called the percentage of time spent in flow control. I should have put an example against it, but flow control is what happens when one of those log-miner processes is waiting for the next process in line to process the data to do something. Okay? And it's really useful. So when you see some of those log-miner processes in high percentage flow control, it can be often indicative that your extract process, remember this is on the source database, your extract process is waiting on I/O to write the trail files, for example. I really need to include an example. Maybe in that data gathering, I should expand that note to include some examples. But if you're not using integrated capture mode of extract, this becomes a mute point because we're not going to even need this. This is only for the 11.203 database with version 11.2.1 of Golden Gate using the integrated capture mode. So we've gathered some basic log file information first, make sure we have no major errors or any major issues. The next obvious thing to look at is automatic workload repository. I've worked for Oracle for quite a while, and my background is just Oracle database stuff. So AWR and Ash is second nature to me. But there's, of course, GoGate being heterogeneous. A lot of people get thrown into the Oracle world just because somebody is buying an Exadata box, so they want to go from some other system into Oracle. So automatic workload repository, AWR, is basically a set of statistics gathering code within the database. At certain frequencies, we take these things called snapshots. And normally when you have an Oracle database, it defaults to creating a snapshot every 60 minutes. But there is a command, GGtuning something or other, I don't know what it is. But you can gather a snapshot. And what that does is it records data on SQL processing layer, I/O layer, foreground weights, background weights, database instance statistics. When you're looking at performance issues with GoldenGate, on the replicat side, this is very important. On the extract side, this can be somewhat important even if you're not running the integrated capture mode, because you're still accessing the source database. I think I'm going to talk about a parameter in a second called DB logging. But AWR tells you what the database is currently doing at the time that snapshot was taken. If you take two snapshots, and I suggest 15-minute intervals at the period that we're interested in, so we have a slow time, let's say the replicat's latency is very high. Take 3 or 4 snapshots at 15-minute intervals, and then we have a script within the Oracle Home, put this in the slide, Oracle Home RGBMS admin directory, called AWR RPT, which says create me an AWR report. Run that script and it basically shows you the number of snapshots you have taken of AWR snapshots. You select which ones you're interested in, just pick 2, and then it will produce either a text file or an HTML file of the deltas between that snapshot and the snapshot after. And that is very good for telling us if your performance and problem lies inside the database or outside the database. And for replicats, this is very important. Okay, for extract, we're going to talk about this parameter called DB log reader for the extract in a minute. That forces us to read the log files through the source database. And that's also useful because you can again see what amount of time we spent reading from the log files through the source database. Active session history takes the AWR data even more granular. I'm really talking on the target side of the replicat processes here. So if you've configured, let's say, a dozen replicat processes, each applying different sets of data, and you see 1 or 2 of them where the latency is getting higher and higher, but you look at the extract and the data pump latency, remember it's distinct processes that are not linked, then you can see that the latency is just on the replicats. The first thing you do is also look at those log files, error report files. Nothing shows up. Next thing you do is you gather some AWR reports from that target database. And with AWR, it's instance whole, right? It's everything that's occurring in that instance, that database at the time that you take the snapshots. So if you have a dozen replicats, it might be more difficult to figure out what each replicat is doing. With active session history, basically it's just an expansion of AWR. It gathers information, or Oracle gathers information for each active session connected to the database. We gather statistics for it at internal intervals. What we're able to do with that is when you look at AWR reports, you look at this bottom example right here. This is just within the SQL layer report for the AWR report. The real nice thing about it is within SQL module, it actually gives you the GoldenGate replicant name. And my replicat is called rep_1a. So by looking at an AWR report on that target database, you can identify within the SQL executions or SQL gets or buffer gets, you can actually see which replicat is causing the slowdown. If you want to dig into that further to get more statistics, like I/O statistics, for example, for the SQL layer, for that replicat process, we have this little script called ash rpti, which was listed in the slide, and that's in your Oracle Home admin, RGBMS admin directory. And that enables you to run active session history reports, but not for all active sessions, for one that you have the SQL module name for. And it will prompt you for that SQL module name. So you can just take that OGG rep name that's listed in AWR, and create just an active session history report for that one replica. That's very clear to see, for example, if you're doing single row manipulations or you're spending too much on I/O on certain objects, certain tables that require attention. Okay, this is a really useful piece of information and a lot of people overlook or just haven't realized they can get. Linked with AWR data. So remember, Golden Gate works traditionally before Oracle acquired it. It's all outside the database, right? All the trail files are stored outside the database. So we need to gather CPU data, I/O data. I didn't include net data, network data. We need our net stat. So for whatever component they're looking at, whether it's extract, data bump, or replica, once we've gathered the log files, the report files, AWR, you need to be looking at the CPU data. And I've just included some examples in here just from limits. You need to determine if we're bottlenecked on CPU or if we're just waiting on something else. So we gather AWR that shows us inside the database. But looking at that, it doesn't tell you if we're waiting on I/O, for example, because of trail file accesses. Remember, they're OS files. So the example is gathering top. I use this -C and -H option because extract and replica, they run in multi-threaded processing mode. So they don't have one process that reads the trail file and one process that applies the data. It's one process but multiple threads of execution within that process. So when you're gathering CPU data, you must gather CPU data for each individual thread within a multi-threaded process. And that happens to be what that -H is for with the top command of that. I/O data, for obvious reasons. We need to find out, when you look at top, for example, and I should write a paper that includes all these examples to make it clear, but when you run top and you find out that replica is only at 25% CPU, you look at AWR. AWR shows it's just using CPU and not doing much else, because it's doing some I/O. But there's no major weights, or no major bottlenecks or contention points. Then we need to look at the I/O data, because it might just be as simple as you have too much contention for your trail files. Remember, trail files have got to be read before we apply the data on the target side. If you put those trail files in a badly contended file system, you're always going to be waiting on the trail file I/O. And it's stored outside the database, so we need to gather I/O data. And to the point about DBFS, earlier today I talked about DBFS with Golden Gate. And because DBFS is the database file system, another one of our priorities, but putting the trail files in DBFS to get the high availability options is fell over between rack nodes, for example. DBFS is just another database. So you need to be gathering AWR reports at those same intervals that you gathered for, say, the replica process for the DBFS instance. Okay, that's important because that shows us the I/O data from the database for DBFS. You also need to be gathering I/O stat data for the file systems where the data files from the DBFS are designed. Okay? So you must include all of this stuff to get a clear picture. I didn't include net stat on here, and I probably should have done. Because with data pump, we don't normally see this, or we don't see this with high frequency. So data pump is reading the trail files on the source, copying them to the target. It's not doing much more than that unless you have various mapping statements to change information from trail file to trail file. But all it's doing is copying data over there. So of course, we need to be gathering some type of network statistics just to make sure that during slow times or increased latency for the data pump, we're not seeing that at times when the network is constrained. Okay, and we must see all of this stuff before we can decide about our performance. Okay, so now we know what data we must gather. I keep saying for support issues, and I'll say this, the escalated issues with Golden Gate that we tend to look at. If we don't have all of that data in one time, it is very difficult for us to discover what the performance problem is. Okay? And you being users of Golden Gate should have the same methodology. You need to gather all of this information at the same period of time to figure out where you're spending your time. That's myself. Okay, so tuning methodology. Kind of talked about this already. Because Golden Gate is decoupled, right? Extract is decoupled from the data pump just because it's somewhat coordinated through the trail file. It's not the same set of processes that are strictly relying on each other at one point in time, right? They can work at different speeds. Same with the replicat process. So the general tuning methodology, and this is, I think, pretty simplistic, is with any kind of database performance tuning, if you've done much of that, you need to identify which is your current contention, which area is causing you problems. And with gathering all of that data that we've already talked about, for an extract, you need to determine if my bottleneck is in mining the log files or writing to the trail files. Because that's what the extract process pretty much does. For the data pump, same deal. It's reading the trail files and writing the trail files. Okay, so as you would imagine for the data pump, you're going to have to see I/O data, CPU data, and the reason for that will come clearly in just a minute, and network data, because that's what it's doing, right? It's reading, maybe manipulating, sending, receiving, and writing. And then with the replicat, it's very similar. We're reading trail files, so obviously it's I/O data we need to look at, and then we're applying the data. And as soon as you start applying the data, you're looking at database information, AWR, active session history, as well as all the CPU and I/O stack data. Okay? Trying to clue yourself into this is the key to figuring out why it's slow. So when somebody says, hey, Golden Gate's running slow today, that for me is like just saying, it's raining somewhere in the country. Right? The next question is going to be, well, where is it raining? And is it important? Same thing with Golden Gate. You have to know where it is, and the way to know where it is by gathering those throughputs and those latency values. Right? If you're using the cloud control 12C, it's very easy to see. So the next few slides, I'm going to use an example. So I talk about, we've got this PeopleSoft payroll. So obviously PeopleSoft is one of our application suites. And this was run last year, and I just been awfully slow in writing a paper to get this out there to talk about this. It's very close to being finished, and I have to do it soon. So the source and the target database, they're all running 11.202 simply because 11.203 was not general release. So I had to run everything on production-ready code. So 11.202 with the databases. Each database, my source and my target, is running on a V2. That was the first Exadata platform using Sun's hardware. V1 was HP, V2 was Sun. It's a quarter rack, and a quarter rack contains 2 compute nodes, so you can run 2-node rack if you want to, running single instance, and 3 storage cells. I'm not going to go into much more detail about Exadata, but each storage cell has 12 disks in it. So it's a pretty good machine to be testing this out. And both the source and the target were configured exactly the same. Version of Golden Gate was 11.111, which is the one before the current release. I think we're on 11.111 something, but that's not important. We're not using the new integrated capture mode because it wasn't available. We're using classic extract. So we ran a payroll paying 500,000 employees. So with PeopleSoft, I'm not a PeopleSoft person by any stretch of the imagination, but with PeopleSoft, the more people you pay, the bigger the payroll is. The obvious. So we took our maximum amount that we had in the PeopleSoft system, which was 500,000 employees. The whole payroll ran in a little under 2 hours, an hour and 53 minutes. And during those 2 hours, it generates 93 gigabytes of video, which averages out about 14 megabytes a second. That's quite a decent rate. So the characteristics of payroll is split into 3 different pieces. First being this thing called a pay sheet, which runs in about 6 minutes. And all that does basically is determine who gets paid this pay period. Okay, so with PeopleSoft, you can, for our testing purposes, we could elect to just pay 200,000 employees. But we did the full 500,000, and this generates about 28 megabytes a second of video generation. All it basically is doing is selecting from a bunch of tables, inserting into a couple of tables and data. Okay, who's going to get paid this period? Second one is pay price, and this is actually the biggest CPU generating stage. And all this does is calculating, based on that list we generated in the first stage, what does everybody get paid? terms of taxes, deductions, social security, everything else. This takes longer at 47 minutes, and this only generates 10 megabytes a second of reading. The final one, which actually takes a lot of CPU power, but also quite a bit of redo generation, is pay confirmation, pay confirm, which basically gets all the data in a state ready to actually write the checks. And again, all this is doing is selecting from tables from the previous stage, manipulating some data, putting it in some other tables. And PaySoft is a very interesting application because it doesn't use Oracle's temporary tables. It does a lot of create table, which is standard DDL database, to create a real database table, populates it with data that we need to do the calculations. When it's finished, it just drops the table. And DDL inside Oracle database can also, it's not the cheapest thing of resources, and it's become even more of an issue sometimes when you're replicating data, especially when it comes to talk about splitting that data up amongst multiple replica processes, especially if one does a DDL against the table that you're already inserting into. So it's something to bear in mind. So we use classic extract, as I said, it was version 11.111.1. We use this thing called the ASM log file read API. Up until this version of 11, Golden Gate would use a different API, which is basically a PL/SQL API to read the log files. The limitation to that is that PL/SQL buffer size is very small. So you'll see many read requests from the extract process to ASM, because if you're familiar with extract, you'll have an ASM login information within the extract parameter. So we're connecting to ASM directly and making these PL/SQL calls, which is a really small buffer size, and it's a limitation within PL/SQL. Version 11 of Golden Gate introduces new log read, and what this does is it connects directly to your source database and reads the log files and the log data, so we can actually go to the log buffer in that source database and not go to the log file at all. It's done through the source database. Now, of course, the buffer size is so much better. I think it defaults to 1 megabyte. So. But it's a much more efficient way of reading the log files in the source database. So I define this parameter, and this is something that you should all check out if you've been using older versions of Golden Gate and you're going to version 11, is this DB log reader parameter. Because of the way PeopleSoft works, I have to tell you, when I first started working on this, I had no idea that PeopleSoft used real tables to do temporary table work. I didn't include the DDL piece, so I didn't replicate any DDL. So of course, all my DML would fail on the target side because the table didn't exist that I was inserting into. Okay, so for PeopleSoft, I had to use the DDL parameters to include all DDL statements. Again, if we're going to use 11.203 database, we should be looking at using the integrated capture mode because it supports the mining compressed data, which we're not using in this environment. A lot of people do use it for Exadata. And if you're going to use that, and this is another thing that we need to understand, is that we have this pool of memory area called the streams pool. Okay? But we're running Golden Gate, and the streams pool is kind of left over inside it's not there anymore. It was used by the Streams product, and still does get used by Streams. There's basically a separate memory area in SJ that the log line server processes and uses to process the log data that it reads from the reading logs before it passes out to the extract process. So if you're using integrated capture mode, I think Joy talked about this earlier in the week, the Streams pool is important to set. If you don't, then it comes out of the shared pool. So, that was the extract parameters. With data bump, I use this thing called a pass-through parameter. And what pass-through does, and I mentioned this earlier today, it basically, all it says is any data that I receive, so any data I read from the trail file, send it to the collection server on the target and do nothing with it. Okay? If you don't have pass-through, for everything that it reads from the trail file, it double-checks to make sure that's something that I'm interested in replicating. My internal test is just on 11.203 database, like that OLTP swing bench workload. Using pass-through reduced CPU by 40 to 45% by that one process.
and increased the speed of passing from source to target by about 25%. That's significant. So looking at that pass-through parameter is well suggested. So again, just the examples of pass-through table, schema name, dot, starch. Just means pass through everything from the PeopleSoft schema. Don't even do any kind of table lookup. Is this something I'm interested in? Just pass it to the collection system. Okay, replicat process. This is the one that actually applies the data on the target side. So just a couple of important points. The first is using a checkpoint table. Checkpoints are something Golden Gate uses to keep track of progress for any of its processes. So for the replicat process, it keeps track of where it is in the trail file that it's reading from to apply the data. Okay? When you use a checkpoint file in the database, and the Golden Gate docs spells it out pretty clearly how to do it, what it enforces is this idea that we can do a commit no wait. And a commit no wait in Oracle Database means that when I say commit, don't wait for the posting to come back from log write to say I've flushed the data from the log buffer to the log file. I'm committed. It basically says, go do it, flush it, and I'll keep on working. And that speeds up the performance of the replicat process is significant. Second thing is this idea of parallel replicat processes. And I have to admit, can be a little daunting. It's advantageous that PeopleSoft has zero referential, with their payroll application, has no referential integrity between its tables. So you will find no foreign keys and no constraints between objects, which makes this so suitable for parallel replicat processes. Now for parallel replicat processes, what I mean is you have one set of trail files and more than one replicat process reading those trail files and applying the data concurrently, because they each have their own set of tables, or schemas, but tables in this example, that they're applying to the target database. So in a simplistic way, you can have one set of trail files and just two replicat processes, and just split the table names up between them so you divide the work. That's parallel replicat processes. What you need to do is, as an example, and there's multiple ways of doing it, but one way to do it is, once you've run the extract process to create trail files, the extract process report file will give you a count of rows manipulated or that we retrieved from that source database for every table that it finds. I don't remember how many it was with PeopleSoft. I think it was 100, let me guess, 105 or something. So in the extract report file, it shows for those 105 tables how many rows were extracted from the source database. Okay? There is a Marathon support note. I should add that to these slides. If you look in Marathon support and look for an article of how to manually parallelize replicats into the title or something like that, give you an example of how to walk through using either a report file like the extract report file, or Golden Gate has this utility called a log dump, when you can dump a trail file and see how many tables within that trail file and how many rows are manipulated into each trail file. That's another very easy way to figure out what the loading is within the trail file. I also talked about this thing called batch SQL. Also in my test, I evenly distributed those table rows amongst 4 different replicat processes. This was just on a first pass to see how performance would be. I also enabled this thing called batch SQL. And what batch SQL does, it enables array processing for the replicant. And you can do this within a little SQL script or PL SQL script, but try inserting 100,000 rows doing insert, commit, insert, commit, insert, commit. Very expensive because each one of those is a CPU operations, right? Go through the buffer cache, have to apply the data, have to go up the log buffer, have to commit, have to wait for a log writer to come back in and continue. When using array processing, what it basically does is builds an array of rows using insert, for example. So you might say batch SQL of 2,000. It'll build an array of up to 2,000 inserts and just do a single insert into using that array name, which basically does one single SQL execution that inserts all the rows in one go. That reduces CPU consumption on that target database substantially. And if you haven't tested, yes, correct. Good question. The question being is, does it adhere to the source transaction boundaries? And you're right, no it doesn't. But for this example, for this payroll, inconsequential. I just wanted to get the payroll data across to my HA front. And you're right, there's limitations limitations. When you use batch SQL, we don't apply the data in the exact same transaction ordering that was applied from the source database. And the reason is because we're trying to reduce CPU consumption through rate processing. And if you think about it, if you have on the target, on the source database, for example, when I ran this PeopleSoft payroll, I used 32 threads of execution. And to think that 32 threads of execution can run in 2 hours, and to assume that one thread of execution on the target could run in that time or less, it's going to be difficult for us to achieve this. So by using batch SQL, you get one step ahead of trying to achieve that result. But you're right, and it's clear in the Golden Gate docs, it actually spells it out very clearly about transaction order. Okay. So just a quick example of batch SQL. Again, it's the number of SQL statements we want to put into each array. Example, we do inserts into table A, updates to A, updates to B, deletes, etc. So we're trying to batch each operation against each table within individual batches. Again, it's for array processing to reduce CPU consumption and time it takes to apply the data on the target side. Can I come back to the question in a little bit? Thank you. Referential integrity is maintained within each replicat process. So if we hit a foreign key constraint within a set of batch SQL statements, array processing, it'll abort out of batch SQL because we won't break any referential integrity rules within the database. In this example, remember, PeopleSoft has no foreign keys. So this was great because batch SQL would work and it wouldn't come out of batch SQL mode because we had no foreign keys to break. Again, if an exception is encountered, like we do find a foreign key, such that the batch array insert touches one of those foreign keys, it'll revert back to normal non-batch mode. Okay, so when I ran this is the first time I ran it with my extract data pump configuration with replicat. I used 4 replicats. And this is pretty clear to see. So this is just latency diagrams. And this is just using GNU plot on Linux, basically going some Perl code run against one of those report files, or the GGtuning. So it shows that for the extract, which is the graph on the left, my latency averaged between 1 and 3 seconds. That's a pretty good latency value, and that was certainly acceptable for the benchmark that we were running. The graph on the right is the data pump latency. And same deal again, it sits at around 3 seconds. Well, for this amount of work that we're generating with this 500,000 people payroll, 5-second latency, or up to 4 or 5 second latency, was absolutely deemed okay. So because of that, I didn't have to spend any more time looking at performance issues with the extract of the data. If I thought, for example, that extract was too latent, then of course I'd have to then go look at CPU data, I/O data, AWR data. But 5 seconds for this large amount of payroll activity was deemed inconsequential, not a big deal. The replicat, on the other hand, was a big deal. So I'm running with 4 different replicats here, and if you can see clearly on that graph, so the left axis, right, is seconds in latency. So you'll see that that very first one, the pay sheet, I go up to almost 230 seconds in latency. Okay. So I'm increasing pretty high there, which is not massive, but still it's a concern maybe if I wanted to keep my latency within seconds. And then towards the end, which is that whole pay sheet, you know, remember getting ready to print the paychecks, my latency increases almost up to 400 seconds. Well, that's just too much. I mean, that's up to 6.5 minutes of latency. Too much. So what you then have to figure out is, okay, well, so by looking at, again, the latency and the throughput, I could have used bit control, the cloud control, and cloud control if I had it. But I didn't. I just looked at those latency reports from the GGtuning file, and I found that the 2 replicats that were causing these issues was this 1C and 1D. Those were the 2 replicats that were causing my high latency. So by looking at those report files, And this is what I was telling you about the extract report files. By looking at the report file, you can see, and this is just one from rep_1c, my third replica. At the end of the run, I can see that this replica has some rather large tables. So one of them is PeopleSoft Pay Special Earnings and the PeopleSoft Tax Balance tables. You can see one of them is what was that? 7.5 million rows, which is just inserts, and then we have 7.5 million inserts, and then almost 6 million updates. Compared to the rest of the objects that just had up to maybe 800,000 or less than 1 million rows per DML type. So I was able to very clearly identify which two tables are causing most of my contention for this particular replica. And to add to that, you can use AWR, like we talked about at the beginning. And AWR shows, if you look at again, this is SQL ordered by elapsed time. So this is how much time it takes to run these SQL statements. You can see the very top one, with 1,795 seconds, is an insert into PeopleSoft Tax Balance. Well, we saw that in that replica report file as one of the heavily inserted and updated tables. So by looking at the AWR report, or Active Session History report, you can tie in the number of rows that are being manipulated by the report file with the amount of loading it's causing in the database. And if you have too many of those objects within a single replica, it's no surprise that the latency is increasing for that particular replica process. So by figuring this out, you can then use this filter, and then you can use a range parameter within the replica parameter file and split one of those tables. And this is an example of using that PS tax balance, which was the highest hit table within the AWR report. I split that table up amongst two different replica processes. So in this example, I have replica 1F1 and 1F2. And the first thing you have to do is identify the unique key columns. Okay, and in this example, just by looking through some of the dictionary tables, I found there was a column called Employee ID that was a unique column. So I can split this very easily by saying, so it just says the at range 1, because it's the first process that's manipulating this table, and the comma 2, it's because it's one of two processes affecting this table, and that's my primary key item. So what the replica basically does is when it reads that trail file, it applies a reproducible, like a hashing function, if you like, against that employee ID, and depending on the value, it'll know which row it's going to say. So it might be like we use a lot in Oracle of hash and then a mod function to figure out whether it's going to apply to process 1 or 2, because the replica parameter file tells you which one. And this evenly distributes the rows amongst those processes. So what then happens when I run at a subsequent time? The graph on the left, which is previously going about very high 4 to 6.5 minutes latency, and the graph on the right, I think my latency is the highest one, it goes up to 100 seconds. So a little under 2 minutes. That's not bad. I mean, that's quite a significant change in performance just from one change. You guys hear that? 5 o'clock is supposed to finish. We've got 5 more minutes. Okay, so this is just a real nice example of how to do this. It's unfortunate that with Golden Gate current, I shouldn't say unfortunate. With Golden Gate current, you have to do this as a manual process. With increasing parallel replicas and splitting data up between parallel replicas, it's up to you to do. If your latency is acceptable, cool and good. I mean, don't keep going, because this can be a time-consuming exercise. If you're out of the latency, you identify by looking at which of the replicas causing the latency problem, what rows are being manipulated via the tables within the report file. And that AWR report is so critical in figuring this out. Without AWR, you might find tables that have more rows, but they might run much quicker than some smaller table rows. And AWR is the only thing that will help you identify. And then you have to go through this iterative process of splitting it up against multiple replica processes, running again to see what I should say, in some future release, I think you should expect that this becomes more automated, just like the whole log liner processing is making things much better for the extract process within the database.
So additional notes, referential integrity is not coordinated between the replicat processes. So when you do have foreign keys, it's up to you to identify them within your application, and then you keep those referentially constrained tables within the same replicat group. For obvious reasons, right? You can't insert into a parent table or child table by replicat 1 when you haven't inserted the parent row yet in replicat number 2. So you need to keep those constrained together. I say remove foreign key constraints if possible. That's kind of like a blasé statement to say that you have control over all the applications. A lot of times it's not possible. Again, I lucked out with PeopleSoft because I was very surprised to find that it doesn't have a single foreign key constraint. Or at least remove the foreign key constraints to enable you to do the performance for the batch SQL and the parallel replicas. Okay, a lot of this comes in with balance. If it's just for a standby site or a reporting site that has truly active, then the business might allow you to remove certain constraints, enable you to have a low enough latency. If they don't allow you to do that, then you might have to settle with high enough latency, and that's what the business decision is. The maximum number of replicats you can have per trail file, I think our documentation says 3, but it's highly dependent on I/O performance of accessing those trail files. So remember, trail files are read from beginning to end. It's sequential I/O. Okay? So depending on, and you might use 3 replicats, and there's no I/O wait at all on your system for the trail files. You put in 35 replicats, and you might see massive millisecond wait time on those trail files. Again, we have no automated way of telling you how to do this. It's up to you to test it, increase replicats, see what the I/O performance is. If you don't gather I/O data, you'll never know. Increasing parallelism is an iterative process. You can parallelize replicats based on schema names, table names, row ranges, as we showed in this example, or a whole mixture of all of them. Again, Golden Gate is so configurable. You can configure this to match your environment. But the thing to bear in mind is that when workload changes, the efficiency of the number of replicats you have can also change. Like I divided up one object, PS tax balance, between 2 replicats. Not that this is likely, but if they increased number of employees to 3 million people, that may no longer be an issue. It might be on some other thing, or if you reduce the number. So as workloads changes, your approach to changing these replicats will change, and that's why you have to monitor the latency and the throughput values. So generally, for my 500,000 employee payroll, the whole replication, which is end-to-end in real time, it completed in less than 2 minutes after the payroll completed. Data pump and extract latency always remained less than 5 seconds, for the most part, I should say, and the replicat latency reached a minute 40, but for the majority of the time it stayed under 10 seconds. If I wanted to keep it under 10 seconds the whole time, I'm sure I could do further parallel replicat processes and continue. But I lost the access to the machine at that point, so I'm stuck at this rate. So, summary. Talk about gathering latency, throughput, database information, and then OS. That's I/O step, CPU data, and network data. Without that first set of information, obviously latency and throughput comes from the report file and the log file, the ggserr.log. Without those 3 bullet points of information gathered at the same point in time, it becomes much more difficult for you or us to help you identify performance issues. Gathering those things is key. Again, work through the tuning methodology, gather that data, find out where the latency is, and zone in on that particular piece. Again, considering using the integrated capture mode for extract, not just for compressed data, we have some performance enhancements in there too, and then batch SQL and parallel replicat processing on the targets. Further information, again, these are just my own support note references. I love this idea that people can take pictures of this stuff and then say, thank God for this. Didn't have to write a thing. People's handwriting is going to get so bad, but that clicking thing is going to be so strong. Anyway, so we have some good references here. Taking pictures. Good. You want me to go next to the slide? And then just we've only got a few presentations being Wednesday. So there's a couple of Gold Game presentations tomorrow. And 8J, because that's my product area. Resources. Okay, any questions? You know, you had your